Nick Tausanovitch, VP Solutions Architecture at Metronome. Metronome is a company that is a pioneer in what we call SmartNICs, basically NIC cards that go in standard COTS servers and provide a variety of acceleration and offload functions. And we've done quite a lot of discussions in the past on SmartNICs. Today's discussion is going to be focused a little bit differently. It's going to be focused not so much on the offload and acceleration aspects of the SmartNIC, but extra functions that can be performed that can support 5G functionality for network slicing. So without further ado, let's get into it. 5G, as I think we all know, will be supporting a very, very wide variety of use cases. The point here is that the use cases are very different, right, in terms of the requirements that they need to get or be supported in the 5G network, and that's one of the reasons why the 5G network rollout is so complex. But I'm going to focus on some of the requirements that are important and in order to be able to support these different use cases, where the SmartNIC can provide some additional benefits. If you look at video, for instance, we might focus on latency as being an important parameter. If we look at broadband connectivity everywhere, obviously that drives a lot of bandwidth through the network that needs to be processed. Mobility, especially in this example with a high-speed train, would certainly drive requirements on the handover and the control plane processing in the 5G network. And then, of course, you have IoT. IoT is not as much about bandwidth, is not as much typically about latency, but it is a lot about scalability, right, and being able to support potentially millions of connected devices. So there's a scaling parameter that needs to be addressed there. And then things like virtual reality, tactile internet. Obviously, that's not just low latency, but I'm calling it ultra low latency in order to get a real good user experience in those types of applications, right? You have natural disaster situations where you need, extreme, what I would say is extreme scalability, right? Going from almost zero to, potentially millions and millions of connections very, very quickly for sustained periods of time. And how do you handle that dynamic scalability? Ultra reliable communications obviously need to have very, very fast detection of problems and very, very rapid response to those problems to ensure the high reliability in those systems. And then of course broadcast services as well. So you have the point here being you have a very wide set of requirements, and all of these requirements have to be met by a common infrastructure, right? Because we all know that in 5G, everything needs to be run on common infrastructure in order to get the economies and the CapEx and the total cost of ownership down. So what's been proposed typically for this is to implement something called network slicing. And with network slicing, you can carve effectively the common infrastructure into different slices that can support these different types of services. So this shows an example, of 3 network slices. There typically would be perhaps many more, and we have different characteristics in those network slices that need to be stringently followed in terms of some of the dynamic behavior. And I'm just showing a few of them here. There would be, obviously many more. But if we look at things like, packet loss, what's the tolerance for a particular KPI in terms of losing some data packets, or jitter, or latency, you're going to get very different requirements in the case of something like Mobile phones, certainly some packet loss is tolerated. You don't want too much latency when you're talking to somebody or doing a two-way video. So latency is important to keep low, but not super low. Some latency can be tolerated. But when it comes to something like autonomous driving, and you have cars relying on data in real time to avoid collisions or get information about proximity to other devices or other cars, you really need to have very low latency, obviously. So we're saying that's ultra low latency is the requirement. Anything above that would not be within tolerance. And then, of course, you might have a network slice that's devoted to the Internet of Things. And there, you're not that concerned typically about latency. Small amounts of packets being reported in from sensors and machines and so on. So what this is trying to illustrate is that you have a very wide set of requirements, and this is just a small slice of those requirements, to use a pun, in these network slices in the 5G environment. So how can we ensure that these service levels are met or KPIs are met? So the first thing is obviously we need to detect any type of interruption or degradation in the service. But the point is we need to do it very, very quickly. If we detect it after the problem has occurred and the service has gone down or the latency requirement has been exceeded, bad things can happen. We don't even want to imagine what effect that might have with self-driving cars. In terms of the infrastructure, we also need to be able to isolate those problems, right? So well-known techniques exist for isolating problems in network equipment, but now in a virtualized environment, how do you isolate problems to virtual machines, virtual switching, isolate problems between the NFVI layer and the VNFs? So that's something that needs to be addressed. And of course, we need to be able to respond to any degradation or interruption in service very, very quickly. And here's a key point. We need to be able to do this without adding a burden on the system, right? Without actually adding more processing requirements into the infrastructure. And we also do not want to add more packet traffic into the infrastructure as well, because that's going to further degrade performance. So we want it to be real-time, non-intrusive, and able to isolate issues between physical and virtual infrastructure. So this slide is basically calling out those requirements as they relate to monitoring and telemetry for a 5G infrastructure to support this type of network slicing. There are many approaches that use control packets, right, or periodic packets to check latency or check connectivity. These things will be too slow in 5G. They will not be fast enough, and they will not scale. They will also induce a lot of control plane processing burden if we do try to make those things happen, in a finely granular fashion. And we need to be able to isolate between NFVI layers, virtual switches, virtual routers, and VNFs very, very easily. So what we've looked at with some of our partners is implementing Inband Telemetry and OANM. So Inband Telemetry and OANM basically is different because it embeds telemetry data within existing packets. It doesn't create new control plane packets. So there's no extra traffic in the network. And it doesn't require control plane processing at the network hops because the telemetry information is carried in band through the network from end to end. So this is very attractive to solve this problem. There are a couple of specs that are in process to define in-band telemetry. There's a P4 spec from the P4 consortium, and there's also an active draft in IETF that's being worked on by many participants. So with in-band telemetry, we can effectively measure these latencies, jitter, look at identify packet loss, and we can do it with very fine granularity, and I will show you some data in a few slides. We can also do things such as service path verification, because one of the nice things about in-band telemetry, since it's traveling with the packet, it's not a separate control packet. It always goes through the path, the routed path of the packets. Sometimes with control packets, they can actually be diverted through different paths in the network, and you may get false results. With in-band telemetry, that's not an issue. And by using things like hop IDs at each hop, you can actually ensure that traffic is going through the network the way that the customer expects. So without further ado, let's talk about some of the details about how this would work. And this shows, we're focusing in here on the compute node because we are a SmartNIC, and that's where SmartNICs are situated in NFV deployment. So in a compute node, you may have a virtualized environment running some virtual machines, typically VNFs in this case. You would have an NFVI layer with some sort of virtual switch, perhaps OVS or some other virtual switching module. And with the in-band telemetry, you can effectively start to look at, use the metadata functionality in the packet and timestamping capability to start to look at things like delay, jitter. You can also look at packet loss and things like that. And because you have the ability to add and delete this data at various points in the chain, you can isolate problems between the NFVI layer, which would be the virtual switch, and the VNFs. So how would a SmartNIC help here? So on the left, on this side of the slide, we basically see the approach where all of this is done in the server in software. So you would have to have, effectively probe points here to look at the data, the metadata, in this case timestamps or what have you, at these different points. So that's an intrusive method. It adds software processing. It adds further delay, and so on. So with the SmartNIC, what we do and what we've done actually is implemented this functionality in the SmartNIC hardware itself. So in this case, we can do the metadata insertion, modification, timestamping, all in the SmartNIC, so the server doesn't have to do any of this processing. So it's completely non-intrusive, doesn't add any compute node at all to the server. And then this is just to orient the audience on the Metronome SmartNICs. If you haven't seen them already, we do have a wide variety of adapters with different speeds and feeds. They are all standard form factor, low profile PCIe cards, plug into standard COTS servers. And we offer a variety of software packages that do virtual switching offload. So we offload Open vSwitch, for instance. We have a package that offloads the Contrail vRouter data plane, and so on. Now, we did a demo with our SmartNIC, and I'm going to run through that quickly here and show you, how it works. It's also downstairs in our booth, in the Metronome booth, so I encourage everyone to stop by and check it out in real time. But effectively, what we did was we implemented a small network with a top-of-rack switch and a server and our SmartNIC plugged into that server. And we created a service chain with two VNFs. We used the in-band telemetry standard from the P4 consortium, which uses a VXLAN GPE encapsulation to carry the in-band telemetry data. And we focused for this demo on latency information. So what we did is at each hop through this path, both physical and virtual, we added we took an ingress timestamp when the packet came in. We took an egress timestamp when the packet came out, and then we did a latency calculation for each hop. And then we took that latency information and we added it to the packet as metadata according to this INT specification. And then at the end of the chain, we picked up the packet, fed it into an analysis tool, which was able to process and then display the information. All of this was done, in the P4 programming language, which is supported by our SmartNICs, and so that's how this functionality was developed rapidly. Now, this just shows basically the path of the packets through the chain. A normal packet may get generated by the test generator and sent into the switch. Then a header gets added, and the latency through the switch is appended, or inserted, I should say, into the packet. It goes through the SmartNIC. The SmartNIC adds its latency to the packet. Then you go through VNF. Now you get the time that the packet came back from the VNF, so now you have the latency through the VNF. You do the same thing with the second VNF in the service chain, and then you go back through the SmartNIC out to the switch. So at the end of this, you have a packet with all of the latency information for each hop, both physical and virtual, embedded in the packet. The physical hops being the top of rack switch. The network interface card we consider a physical hop because it's going through basically the card. So we call that a physical hop. And then when it goes through the VNF, that's a virtual hop. And this basically is showing you the implementation in the demo in a little bit more detail. But this is basically showing you the points of timestamping that we used to calculate these latencies, and how things were output to the analysis tool. And this shows effectively the output of the analysis, or the output of the analysis tool. By the way, we used Splunk as the analysis tool, and it's very powerful for this type of an application, and does very good basic analysis of the data. But what we found here, and this is key, is if you look at the bars, you'll see that the small orange here, I believe, is the switch. The small purple here is the NIC traversing the NIC card itself, and then coming back out. But the big dominant terms are VNF1 and VNF2. So we've got the green and the red is VNF1 and VNF2. And so what you see is that the dominant factor in latency is the VNFs, not the switch hardware or the NIC hardware. And this is very interesting. And what you can do is histogram the latency over time, and this is completely granular because it's looking at every packet, and you can record this for as long as you want and look back in time and see if problems occurred. And you might see something like spikes occurring, right? And then you can isolate problems. And this is actually something that we've used to isolate real-world problems that can be caused, for instance, by a microburst of packets overloading a virtual networking function, right? And then the latency goes up. Or it could be because the virtual networking function is being bogged down. Sometimes interrupts come in, and you don't know why a VNF is taking longer to process packets. So this is a very, very powerful tool for troubleshooting and also isolation between different VNFs and the NFVI layer. So takeaways and next steps. This is the first step, hopefully, of a lot more future work in this area. The next step for us will be to integrate these telemetry capabilities in with our standard production software offerings that we have today for OVS, vRouter, and the Cornic software packages that we have. And then there's many other things that we can do besides just latency or timestamping. We can look at link utilization reporting. We can look at queue occupancy, congestion status. We can use packet sequence to look at the packet order and detect if packets are being reordered somewhere in the chain. And then support different types of encapsulation formats for the telemetry besides VXLAN GPE. The specification calls out IPv6 and NSH as possible encapsulation formats. And then the next step would be to really make this much more automated and closed loop, right? So that you can have self-healing networks down to the VNF level of granularity. If a VNF fails, you can migrate to somewhere else. And also to be more predictive instead of reactive, be proactive and ultimately predictive by allowing a dynamic scale out based on a degradation in service. Machine learning can be used to make this predictive, so you can correlate things like latency with time of day and user traffic profiles to sort of predict when a failure might be imminent, and then take some proactive action by scaling out more resources before that occurs. So that's, I think, it, and it looks like we ended just on time. And thank you very much, and if you have questions, please stop by the booth. We'll be happy to talk to you. Thank you.